Welcome to Chem Time.
Hello friends, welcome to the presentation. Today's presentation is application of first law of thermodynamics to an open system under steady state conditions. The presentation is useful to chemistry students. This presentation is also useful to engineering students of chemical, mechanical, petroleum and agricultural. I start the presentation by highlighting the importance of today, that is 22nd June. In the year 1792, on 22nd June, James Nielsen was born, and Sir has patented the use of hot air blast instead of cold air blast for the smelting of iron. This patent has reduced the amount of coal that is to be used. Coming to the presentation, in this presentation, we are going to cover the concepts which are the difference between steady state and unsteady state and application of first law of thermodynamics to an open system under steady state conditions, which include the power generation calculations of a turbine and difference between the nozzle and diffuser. Coming to the difference between steady state and unsteady state. In case of steady state, the transport properties like velocity, temperature, and pressure do not vary with time at a given location. If the transport properties at a given location vary with time, we call that state as unsteady state. The, the general energy balance equation for steady state system is given by m dot into delta H plus delta U square by 2 plus G delta Z is equal to Q plus Ws, where m dot is mass flow rate, and this can be calculated by the formula rho V E. Rho is density, V is average velocity, A is area of cross section. Delta U square by 2 is specific change in kinetic energy. G delta Z is equal to specific change in potential energy. Use of this particular equation is explained through the following problem taken from Introduction to Chemical Engineering Thermodynamics by Van Ness and Smith. The problem is steam at 1400 kilopascal and 350 degrees centigrade, designated as state 1, enters a turbine through a pipe that is 8 centimeters in diameter at a mass flow rate of zero point 0.1 kg per second. The exhaust from the turbine is carried through a 25 centimeters diameter pipe and is at 50 kilopascal and 100 degrees centigrade, that is state 2. What is the power output of the turbine? Assume that there is no change in potential energy. The data that is given is the at state 1, the specific enthalpy of steam is 3150.7 kilojoules per kg. The specific volume is 0.20024 meter cube per kg. At state 2, the specific enthalpy is 2682.6 kilojoules per kg and specific volume is 3.4181 meter cube per kg. We need to calculate the outlet and inlet velocities based on the following formula. Velocity is equal to mass flow rate by density into area of cross section. But 1 by density will be specific volume. As a result, velocity will be mass flow rate into specific volume by area of cross section. The area of cross section can be calculated as pi by 4 into diameter square. The velocity at the inlet based on the inlet pipe diameter of 8 centimeters and a specific volume of 0.20024 meter cube per kg and mass flow rate of zero point 0.1 kg per second can be calculated as mass flow rate into specific volume divided by the area of cross section. So 0.1 kg per second into 0.20024 meter cube per kg divided by pi by 4 into 0.08 meter square. 0.08 is the inlet diameter, which gives rise to the inlet average velocity as 4 meters per second. The outlet diameter is 25 centimeter, that is 0.25 meters. The specific volume is 3.4181 meter cube per kg. The mass flow rate is 0.1 kgs per second. With this, the outlet average velocity is 0.1 kgs per second into 3.4181 meter cube per kg divided by pi by 4 into 0.25 square, which gives rise to 7 meters per second. As a result, the specific change in kinetic energy is V2 square minus V1 square by 2, that is 7 square minus 4 square by 2, that is 16.5 meter square per second square. Now, the units of meter square per second square can be expressed in kilojoules per kg. This can be done by multiplying the numerator and denominator of 16.5 meter square per second square by kg. So, as a result, 16.5 meter square per second square becomes 16.5 kg meter per kg second square. This can be written as 16.5 kg meter per second square into meter into 1 by kg. All of us know kg meter per second square is Newton, Newton meter is joules. As a result, 16.5 meter square per second square becomes 16.5 joules per kg, which can be expressed in terms of kilojoules per kg, that is 16.5 into 10 power minus 3 kilojoules per kg. There is no heat transfer. As a result, Q will be 0 and there is no change in potential energy. So delta Z, G delta Z is equal to 0. With this, the first law of thermodynamics for an open system under steady state conditions becomes m dot into H2 minus H1 plus delta U square by 2 plus 0 is equal to 0 plus W. With the calculated and given numerical values, the equation becomes mass flow rate is 0.1 kgs per second into 2682.6 kilojoules per kg, that is exit enthalpy, minus 3150.7 kilojoules per kg, that is inlet enthalpy, plus 16.5 into 10 power minus 3 kilojoules per kg, that is change in kinetic energy. That will be equal to Ws. So Ws will be minus 46.81 plus 16.5 into 10 power minus 4 kilojoules per second, or minus 46.8 kilowatts. Since work is extracted from the turbine, Ws is shown as the. If we look at the problem and the magnitude of the specific enthalpy change and specific change in kinetic energy, the specific change in enthalpy is minus 468.1 and the specific change in kinetic energy is 16.5 into 10 power minus 3. So this shows the specific change in enthalpy is much higher than the specific change in kinetic energy. So that is why many of the problems given assume that the change in kinetic energy and potential energy can be neglected. So the second problem is given in 8 2004 for chemical engineering. And the problem is, consider steady state flow of air of specific heat at constant pressure 1005 joules per kg Kelvin in an adiabatic passage. Air enters the passage at 100 kilopascal and 500 Kelvin with a velocity of 150 meters per second and leaves at 510 Kelvin. Assume air to be an ideal gas and neglecting gravitational effects. The passage is. There are four choices given. The choices are diffuser, the velocity at the exit is 49 meters per second. Diffuser, the velocity at the exit is 79 meters per second. Nozzle, the velocity at the exit is 179 meters per second. Nozzle, the velocity at the exit is 249 meters per second. We have to find out one of the correct options. First of all, the difference between nozzle and diffuser need to be understood. A nozzle is a device that increases the velocity of a fluid at the expense of pressure, and a diffuser is a device that increases the pressure at the expense of the velocity. So, if the calculated exit velocity is less than the initial velocity, then the passage is through a diffuser. The calculated velocity at the exit is greater than the inlet velocity, the passage is through a nozzle. So, first law of thermodynamics written for this particular case is delta H plus delta U square by 2 plus G delta Z is equal to Q plus WS. For adiabatic process, Q is equal to 0 and there is no shaft work, Ws is equal to 0. And it is also stated gravitational effects can be neglected. So the net result is G delta Z is equal to 0, which simplifies the equation 1 to delta H plus delta U square by 2 is equal to 0. Writing in terms of specific heat and the velocities at the inlet and outlet, the equation becomes Cp into T2 minus T1 plus V2 square minus V1 square by 2. Given T2 is equal to 510 K and T1 is equal to 500 K, Cp is 1005 joules per kg Kelvin, V1 is 150 meters per second. With this, we can write the equation, simplified equation as 1005 joules per kg Kelvin into 510 Kelvin minus 500 Kelvin plus V2 square minus 150 square by 2 meter square per second square is equal to 0. So just now we have shown meter square per second square can be written as joules per kg. So as a result, V square by 2 will be 150 square by 2 meter square per second square minus 1005 into 510 minus 500. The joules per kg there will be replaced with meter square per second. So V2 square by 2 will be 1200 meters square per second square. V2 will be 49 meters per second. Since the velocity is reduced compared to the inlet, the passage is through a diffuser. With this, I conclude my presentation. Thank you. Request you to like, share and subscribe my channel.